So this video goes over the Unit 4 practice assessment questions on the Google form. So the first question says we have 10 grams of each of these compounds, which contains the lowest mass of chlorine. So in order to find the lowest mass of chlorine, we just need to take our 10 grams and divide by the molar mass of these substances. And we know that the highest molar mass will give us the smallest moles of Cl. So if we take a look here, the AgCl has the highest molar mass. So that will be the answer right there. Second question, we have we want to determine the identity of unknown metal X, which is in this XBr. And we have here the grams of XBr. And if we can figure out the molar mass of XBr, the grams per mole, we can figure out what X is. So in order to do that, we have to go through the precipitate. So I will find how much precipitate was formed by subtracting off the filter paper here. Get 1.880 grams of AgBr. If we look at a reaction between XBr and AgNO3, we'll see that the ratio between the AgBr and the XBr is 1:1. So 1:1. So whatever moles of AgBr were formed, we get this. It came from the same number of moles of XBr. So I can take my 1.88 grams of AgBr, divide by the molar mass, which is given to us. And that will give us 0.01 moles of AgBr. That means we also have 0.01 moles of XBr. Here we have the grams, so the molar mass of XBr is equal to the grams of XBr per mole, and the grams of XBr are 1.030 grams, and the moles are 0.01 moles, so this is 103 grams per mole. And if we look at the periodic table, the mass of bromine is 79.90 grams per mole. So subtracting that off, 103 grams per mole minus 79.90 grams per mole, we'll get something very close to 103 minus 79.9, we get 23.1 grams per mole. So I'll look at these ions in group 1, and the element closest to 23.1 is sodium. Next problem, we have 3.0 moles of CS2 and 16.0 moles of H2. So several different ways to do this limiting reactant problem, this Stoich problem, and it says that after one of the reactants has been totally consumed, how many moles of H2S have been produced. So we want to know the moles of this, but first we need to find the limiting reactant. So one way to do this is to say, oh, well, 3.0 moles of CS2. I know that if I multiply by 4 moles H2 over 1 mole CS2, I get 12 moles H2. So that means that I would need 12 moles to react all of the 3 moles of CS2 away. We have many more moles than 12 here, so this is my excess, and this is my limiting reagent. Okay, so taking a look at this, I know that this is my limiting reagent, so I'm going to base my moles of H2S off of that. So 3.0 moles of CS2, and then times 2 over 1, right? Because we're changing to our H2S, 1 mole CS2, and we get 6 moles right here. The other way we could have found the limiting reactant is by taking 3 divided by 1 is 3, 16 divided by 4 is 4, and that means that we have less equivalent moles of CS2, and so that would be the limiting reagent, as we found before. Next question, it asks the number of NO3 ions that react has to be equal to which of the following. So if we take a look at the NO3 right here, it is not true that 10 times the NO3 is not 10 times the H+. It's actually 1/10. If we take a look, 3 times the number of water molecules that are produced, well, the NO3 again is not 3 times the amount of water produced. Okay, it is 1/3 of that. It is 1/4 of the zinc, right? The ratio of NO3 to zinc is 1:4. So here is the correct answer here. This next problem, we want to, again, it's giving us some reactant amounts, and the reactions complete at these conditions right here. This is STP, actually. That's a good thing to recognize, that we're at STP. And we need to figure out which one of these is true. So if we take a look here, we've got 2Al and H2SO4. And if we look up here, we can find the moles of H2SO4 by taking 0.3 liters times 1.0 moles per liter. And we get 0.300 moles of H2SO4. All right, so we've got 0.3 moles of H2SO4. For our aluminum, if we take 2.7 grams of Al and divide it by its molar mass, which is 27 grams per mole, this is 0.1 moles of aluminum. So 0.1 moles here. So there's a bunch of choices here. And so we're going to take a look, first of all, before we look at the choices even, because I see a bunch of products and things that are happening, I want to figure out what the limiting reagent is. So if I take my 0.1 moles of Al, divide by 2, I get 0.05 moles of Al. If I take my 0.3 moles of H2SO4 and divide by my coefficient of 3, I get 0.1 moles of H2SO4. The aluminum is smaller, the equivalent moles are smaller, so this is our limiting reactant, our 0.1. So I'm looking at the answers here, and I think it might be easiest if we just stick this into a BCA table and figure out what happens here. So if I take my 2Al plus 3H2SO4 and I form aluminum sulfate plus 3H2, and I start out with my 0.1 moles here. And I start out with 0.3 moles here. 0, 0. I know that my aluminum is the limiting reagent. I'll subtract that off. Here, my ratio is 3 to 2. I need to take 0.1 times 3 halves, 3 over 2, and that will give me minus 0.15 moles. So we have 0.15 moles left over. Here, my coefficient is 2 to 1. So for the aluminum sulfate, I would take a half of this. So that would be plus 0.5 moles. Here, the coefficient is the same as the H2SO4. So whatever this changes, that's the same change, except it's positive. So there we go. We've got our BCA table. Now let's look at the answers. It says H2SO4 is in the excess and 0.15 moles. Well, that is the answer. That one fits. So we don't need to check any of the other ones. And clearly that's wrong. The second one is wrong. And 6.7 liters, that sounds a little bit too high because we're taking this times 22.4 liters per 1 mole, and that would give us a smaller number than 6.7. All right, this next problem is a particle model problem. If we take a look here, we're getting, this is a total of 8 CO2s, and this is 10 H2Os. A hydrocarbon is something with carbon and hydrogen. So if we look at our numbers of carbon, it would be C8, and the H is 820. The question asks for the empirical formula, which is the smallest whole number ratio. The simplest, not smallest, simplest whole number ratio. If we look here, that would apply to the C2H5. This next problem, we've got a precipitation reaction. So if we look here, the strontium and the sulfate are reacting. And so the sodium and the acetate are spectator ions. So if we look here, spectators, that is definitely not true. This can't be true because they're reacting. So it could be sodium and acetate. Sodium acetate is the insoluble precipitate. That is not true. That's the aqueous one. So the correct answer is this. And then a follow-up question is, what's the correct net ionic for the reaction? Again, here, right, the formation of the precipitate is the reaction. That's what's driving the reaction. So those two ions forming the strontium sulfate make up the net ionic reaction. This next one, we've got nitric acid to sodium carbonate. And it says here that we've got 0.4 moles of CO2 is produced. It's asking what's the original molarity of the sodium carbonate solution. So we can work backwards here to figure out what the amount of sodium carbonate is. Notice here an excess. This is the excess right here, and this is the limiting reactant. So we can go from the 0.4 moles of CO2 and use stoichiometry. Can go back here. We can see that it's just 1-to-1. So 1 mole Na2CO3 over 1 mole CO2. That equals 0.4 moles of Na2CO3. Okay, so then to find the original molarity, we need our molarity equation, which is moles per liter. And so I can put in my 0.4 moles and divide that by my liters of solution. That was 0.2. And so 0.4 divided by 0.2 would give us 2 molar. This was a review question. So to find the empirical formula, remember we can take our percents, pretend that they are grams, and we will divide this by the molar mass of nitrogen to get moles. So 14.01 grams per mole. This is nitrogen. So dividing 30 by 14.01, we get 2.14 moles of N. Our 70 grams of oxygen is divided by 16 grams per mole. And we get 4.38 moles of oxygen. Divide these out by the smaller number of moles. That would be 2.14. This gives us 1 mole of N. This is very close to 2 moles of O, so our formula has to be NO2. Another review question with mass spec. We want to figure out the identity of this element. The mass of this element is between 35 and 37. So taking a look at the periodic table, that would be closest to chlorine. Chlorine has a mass of 35.5 roughly. So that would be kind of closer to the 35. So we can see that the abundance is higher here. So here we have a particle model problem. So it says that we have x2 plus y forms xy. And when we balance this, we need 2x here and a 2y. And this is kind of misleading. This is not a balanced reaction. It's just saying that we have 2 x2 molecules and 3 y atoms. So here we can see that each x2 and 2 of the y's, so let me grab a x2 and 2 of the y's, that will form 2 xy's here. Okay, so we need at least 2 xy's. Here we're going to rule out this one because that has no xy in it. And then what's left over here, so this red atom can attach to one of the blue atoms and form another xy. And there will be one blue atom left over. Okay, so those will make another xy and have one blue atom left over. So A is the correct answer. Next problem, and I believe this is the last problem, we've got calcium and hydrochloric acid reacting. And question is, what will be the effect on the amount of gas produced if the experiment is repeated using 0.4 grams of Mg instead of 0.4 grams of calcium? So if we divide these by their molar masses, we'll get the moles of these things so that we can take a look at the balanced reaction. This is 0.01 moles of calcium, and this is some amount that's greater, I'll just say greater than 0.01 moles. So more than that. And then if we look here, we have our 0.125 liters times 2 moles per liter for our hydrochloric acid. So that's our 0.250 moles of HCl. So we can see here that 1 mole of calcium, the 0.01 moles of calcium, and is clearly the limiting reagent here in this case. And if we add in this amount of magnesium instead, this is about maybe about 0.02. We can calculate it exactly, but let me just do that. But I believe it's going to be about 0.02. Yep, it's like 0.016. So if we replace that, here's our calcium. If we replace this with magnesium instead, we would have 0.016 moles of magnesium. If we compare it to our 0.250 moles of HCl, that's still going to be the limiting reagent, okay? Even if we replace it with magnesium, which is more moles. So we should get exactly the same amount of gas produced, even if we replace this with magnesium. Magnesium will react in the same way. It'll have the same stoichiometry. It's just that it will form magnesium chloride instead of calcium chloride. So we should not expect any change on the amount of gas. So let's see. Both metals will produce equal volumes of gas. Balanced net ionic reaction. So if we take a look at our reaction up here and split it up into its ions, we have to split up the strong acid because it's a strong acid and completely dissociates. We need to split up our aqueous. Oh, missing a 2 here. And we have H2 gas, which we do not dissociate. We can see here the Cl minuses are canceling out. So let's find the correct net ionic here, and I see that it is right here. Okay, and I believe that is the last question. Let me just check. Yep. Okay, so if you have any questions on these solutions, let me know.